Welcome to this video on the combined gas law. In previous videos, we've talked about a few different gas laws, most namely Boyle's law and Charles's law, which try and relate a few different characteristics of gases together in a quantitative way. And so we saw, for instance, with Boyle's law, maybe I'll put a little b over here, that pressure and volume were inversely proportional. So when we increase pressure, the volume of a gas decreases and vice versa. With Charles's law, we saw that temperature and volume were directly proportional. So when we increase the temperature of a gas, if pressure was constant, volume increased. And if we just increase the volume of a gas with constant pressure, then temperature increased. But there's a third combination of these three variables, pressure, temperature, and volume, which we haven't yet explored, and that's pressure and temperature. So what happens to a gas if we increase the pressure, maintain constant volume? We want to ask what's going to happen to the temperature and vice versa. If we increase temperature, maintain constant volume, what happens to the pressure? And to look at this, we're just going to examine an everyday situation, which I hope all of you are familiar with, and that's the case of a basketball on a hot day and on a nice chilly morning. What happens to these basketballs? Well, in the latter case, we know that if we try and bounce a basketball when it's really, really cold, it's just going to sort of dribble up a little bit. It's not going to be very useful. It's going to be extremely unsatisfying to bounce a cold basketball. But in contrast, if we try and bounce a hot basketball, it's really going to bounce really, really high. It might even be unplayable. And so this is interesting. Let's take a look at what's happening at the molecular level. So let's zoom in on the wall of the hot basketball. So if this is the wall of the hot basketball, first that we know that the volume of the basketball is constant. We can't really manipulate this thick rubber that is the basketball. So when we increase the temperature, of the basketball, we know that the little air particles inside that we've pumped inside are going to move faster. Because that's all temperature is. It's the speed of gaseous particles. And if they're moving faster, they're going to collide with the wall of the basketball, both at a greater rate, so more times, but also with more strength. If they're moving faster, they're going to transmit more energy to the container, to the walls of the basketball. And conversely, if you look at the cold basketball, we zoom in on the cold basketball, we're going to see that these particles don't have anywhere near as much energy, and so they're just sort of flopping against the edge of the basketball. You may even be able to compress this basketball a little bit because there's so little energy within these gaseous particles inside. And just to sum up this discussion, if we have more force pushing against the container of a gas, well, we just call that pressure. That's really what pressure is, and we'll take a look at that in more detail when we look at the kinetic molecular theory. And so we can definitively state that the hot basketball has a greater pressure than the cold basketball. So when we've increased the temperature, in this case, hot is an increase in temperature, we have also increased the pressure. And in this case, we've decreased temperature and we've decreased pressure. So we can summarize our little statement right here and say that, oops, that's my virus definitions. We can say that pressure and temperature are directly proportional. So when we increase one, we increase the other, and vice versa. But now let's just summarize again, a little more mathematically, sort of the three gas laws which we've just developed. With Boyle's law, we said that pressure and volume were inversely proportional. And so we can express that by saying P, which represents pressure, times V, volume, is a constant. And that's sort of counterintuitive. You think, well, if I'm multiplying together, doesn't that mean they're directly proportional? But I'll quickly show you that it means they are inversely proportional. So say we've got something with a pressure of 2 arbitrary units and a volume of 5 arbitrary units. Well, then that's going to equal a constant of 10. What happens if we double the pressure in this sort of random gaseous system? We're going to have a pressure of 4. We still need to have that constant. Remember I told you P times V equals a constant, so this expression is still going to be equal to 10. But we have to change this 5 a little bit, because if we kept it at a constant 5, well, 4 times 5 is 20, and that's not equal to 10. So we actually need to halve this 5, make it 5 halves, for the constant to be held constant. And so what this means is when we increase the pressure in this system, we have to decrease volume to maintain the constant. And so that's why when you multiply two different variables together and set them equal to a constant, you're expressing that they're inversely proportional. And similarly, for V over T, or something over something else, that kind of relationship expresses direct proportionality. So we saw this was Boyle's law up here. We saw with Charles's law that volume and temperature were directly proportional, so increasing volume increases temperature at constant pressure. And similarly, this was this last gas law up here, which we just defined. We saw that pressure and temperature were directly proportional. And you might see this referred to in some textbooks as Guy-Lussac's law, but that's pretty rare. And so you can just sort of always derive this relationship from the basketball analogy, or just simply memorize it. But now that we've got these three relationships, we can solve a great deal of problems. We can solve problems which involve changes in pressure and volume, changes in volume and temperature, etc. But maybe we want to combine all these expressions. This is the video for the combined gas law, after all. So let's take a look at how we combine these. We see that in both cases, we see P and V show up in the numerator of this fraction, whereas T is in the denominator in both Charles's law and what we can call Guy-Lussac's law. And so maybe we can combine it something like this, P, V over T. And I'm going to tell you that we can. We can actually say that if we have one state of a system, we look at a system in a specific instant, the pressure, volume, and temperature expressed in this way, so pressure times volume divided by temperature, in this first state is going to be always equal to the pressure times the volume divided by the temperature of the same gaseous system in a different state. So we can say P1 times V1 over T1 equals P2 times V2 over T2. And yes, ladies and gentlemen, this is the combined gas law. And we can use it to solve all manner of problems. Say we have a problem which gives us information about the pressure, volume, and temperature in one state, and the pressure, volume, and temperature, or the pressure and volume in another state, then we can find the temperature. So given 3 of these variables and 2 of these variables, we can always find the other one, the missing one. Say we're told that pressure in a system is kept constant, and we're only dealing with volume and temperature on both sides of the equation. Well, we can still use the combined gas law instead of resorting to our more individual gas laws up here. We can simply just cancel pressure. We can just cancel pressure out of our equation, and we get V1 T1 is equal to V2 over T2. So we can use the combined gas law in a whole different bunch of situations, whole bunch of calculations. And I'll show you one example here. So let me read it to you. In a room held at constant pressure, the temperature is slowly increased from 20 degrees Celsius to 40 degrees Celsius. I want you to find the new volume of a balloon which measured 5 cubic meters in volume at 20 degrees Celsius. So press pause, take a stab at this problem, and I'll be waiting to go over the answer with you. Alrighty, welcome back. Let's see if we can take a stab at this problem using the ideal gas law. So first we see that we're talking about 3 different kinds of variables. We've got pressure, we've got temperature, and we've got volume. And so that should trigger something in your brain that, okay, I should be using the combined gas law. So let's write out the combined gas law, see if you remember it. We have P1 times V1 over T1 equals P2 times V2 over T2. And the first thing we're told is that a room is held at constant pressure. And like we just did, we can actually cancel out the pressure on both sides of the equation, because say this is equal to some number, it's going to be equal to the same number over here, and we can just algebraically divide out that expression, that number, from both sides. Okay, that's well and good. Now we want to see what we're trying to find. We want to find the new volume of a balloon which measured 5 cubic meters at 20 degrees Celsius. So new volume, the volume in the new state, is going to be V2. So we need to solve for V2 in this expression. And we can do that quite easily simply by multiplying T2 by both sides of the equation. So that's going to cancel out on this side. And we're going to get V2 is equal to T2 times V1 all divided by T1. And let's see if we know these three quantities. If we know these three quantities, then we can simply solve for V2. Well, we do. We know that V1 is 5 cubic meters. We know T1 is 20 degrees Celsius, and we know T2 is 40 degrees Celsius. But we need to be careful. We can't just plug in these temperature values. Like any gas law, you always have to input temperature values in Kelvin. But that's pretty simple. We can convert degrees Celsius to Kelvin. So 20 degrees Celsius, we can just add 273 to that. That's the conversion factor to get Kelvin. So that's equal to roughly 293 Kelvin. Similarly, 40 degrees Celsius plus 273 is equal, let's see, to 313 Kelvin. Remember, we don't say degrees Kelvin, we just say Kelvin. And we know that the initial volume is 5 cubic meters. And so now we can plug in these values into our equation. V2 is equal to 313 times 5, all divided by 293. And so we get, if my calculations are correct, to two significant figures, 5.3 cubic meters for the new volume. And let's just do a little sanity check on that number. What have we done here? We've held it at constant pressure, and we've increased the temperature of a balloon. And so we know, if we go up to our combined gas laws, that temperature and volume are directly proportional. So we've increased temperature. What should happen to volume? Well, volume should increase, and in this case, volume is increased from 5 to 5.3 cubic meters. So that answer makes sense. Alright, thank you very much, and I'll see you in the next video.